Welcome. Today we shall be looking at logistic regression. In this lecture, we shall look at how logistic regression is used to model a binary outcome, overcoming the limitations of linear regression when the dependent variable has only two values. We shall look at how we use logistic regression to predict the probability of an event by fitting an S-shaped curve which can be linearized by transforming the outcome into the natural log of the odds, or the logit function. There are certain key considerations which we shall also look at, which include model building through methods like backward elimination, creating dummy variables for categorical predictors, and testing for interactions between variables. When do we use logistic regression? What properties do we find in logistic regression? How do we interpret them, the results? How do we build a model? What are dummy variables? And when we say interaction of variables, what do we mean? So these are the objectives that we seek to achieve in this lecture. So logistic regression is one of the most commonly used statistical methods in medical research. And there's key reasons for us to use logistic regression. We use logistic regression to identify variables that are significant predictors of outcome, independent of the effects of other variables. So we use it when we seek to control for confounding factors. We can also use it when we seek to determine if a specific variable is related to an outcome while controlling for the effect of confounding variables. So, like I've just said. Remember, we've been looking at regression analysis. We started with linear regression. We looked at regression as a whole. Then we went on to linear regression, and then we looked at data transformation. And so we've moved into this particular stage where we're looking at logistic regression. But overall, we use regression techniques to predict the value of one variable based upon the value of other variables. And to do so, we develop an equation which predicts a dependent variable y, giving a value for an independent variable x. And then we extend this to look at multiple independent variables, x1, x2, x3, so on, all the way up to xn, that may affect that outcome y. So in a nutshell, this is what regression is about, whether we're doing linear regression or logistic regression or Poisson regression or Cox regression, and there are different regression methods. So but this is in a nutshell what it's about. So we're developing an equation that predicts the value of a dependent variable for any given value of the independent variable x, and of course we can include multiple independent variables in that equation. So the outcome variable is y. If it happens to be continuous, then we use multiple linear regression. If the outcome variable is dichotomous, binary, that is, it takes two levels, then the multiple linear regression approach is not going to work. It's not going to work. So we need a model that can permit only two values of y, because the dependent variable takes only two values. Remember, it's binary dichotomous, so it's either present or absent of whatever value that is in consideration, So we need to develop a model that can permit only two values of x. So examples of variables that have a binary outcome: mortality, disease outcome, event occurrence. So in logistic regression, the dichotomous variable outcome variable is coded as a 0 or 1, and the value of 1 indicates the presence of that disease or event or mortality. So 1 is yes and 0 is no. So we need to bear this in mind, that this is how the outcome variable in logistic regression is coded. It's 1 or 0, 1 indicating the presence and 0 indicating the absence. There are no in-between values. Certainly the outcome variable is not like Schrodinger's cat, which is neither alive nor dead. So remember that we use proportions in descriptive statistics for dichotomous variables, and the proportion is basically a mean of the zeros and ones for that sample. It also represents the probability of a subject having the event. So that's a probability of drawing a subject with a 1 from the sample. So the proportion is actually a probability of an outcome, and it's the proportion of ones. Now remember that the permitted value of p ranges from 0 to 1. You cannot have negative p, and it certainly cannot be more than 1. So in regression, p represents the probability of an outcome based on the values of the independent variables. And so that's what it is for us in logistic regression. So let's consider this example that seeks to predict gender based on height. So the prediction of male sex based on height. So it's saying, look, given a certain height, what is the probability the person is male? So if you look at this graph on the y-axis, it gives us the proportion of males at any given height. And if we were to plot that line, we will find that as height declines, the proportion of males within the sample also declines. So this is really what this graph is showing us, and these circles just show us the relative proportions that are male at each given value. So for example, at this height of in inches of 60, we come up here and we find that the proportion of males is probably going to be less than 5. Certainly at this value here, it says for this particular height, half the observed values are male and half are female. So that's what this 50-50 here is representing. At this value of height, 70% are female and 30% are male. So and so on. And at this point here, this value of height, 95% are male and only 5% are female. So when you draw the regression line, you discover that it is not linear. It follows a curvilinear pathway. And what this tells us is very simple. Remember that the y value is either male or female. There is no in between. So it's telling us this, that they all fall on 0 or 1, where in this case 1 represents male and 0 represents female, that is not male. So you see this. So the values, observations are either all on this line or on this line. There are no observations in this space in between, because the value is either 1 or 0, as the case may be. So all these intervening values are actually not necessary. So it's either 0 female or 1 male. So it's either going to be here or there, and then if you take the relative proportions and try to fit a line, it's going to go curve in between like that, sort of like S-shaped. So this is the problem if we were to use linear regression, right? If you use linear regression, it's going to give you predictor values that are greater than 1 and less than 0. However, the problem with this approach is that these values are theoretically inadmissible, because the actual values are either 1 or 0. So 1 means male, 0 means female. So if we were to apply a linear regression to this problem, our predictor values, we're going to have values above 1, which does not make sense, and values below 1, that is negative values, which also do not make sense. Doesn't mean anything, and so that model fails. It doesn't work. predicted values cannot be greater than 1 or less than 0. And so this is the problem with trying to apply linear regression when the dependent variable has only 2 values, because the assumption of regression of constant variance does not hold. It's not the case with a binary variable, because the variance for a binary variable is given to us as p times 1 minus p. So in other words, the variance will change depending on the value of p, right? Depending on the value of p. So look at it. So when 50% of the people are 1s, then the variance is going to be 0.5, because this is 0.5 times 0.5, and that's the maximum value of the variance. So at more extreme values, the variance decreases. So if, for example, p is 0.1, the variance is just going to be 0.09. So this tells us that as p tends to 1 or tends to 0, the variance is going to tend to 0. So already this key assumption of linear regression of almost stochasticity is already broken. So linear regression does not work for binary outcome variables. The other problem is that the predictor values are not normally distributed, because the significant testing for regression coefficients is based on the assumption that the errors are normally distributed. But this is the problem now. The values of y can only be 0 and 1. So the assumption of normally distributed predicted values or errors of prediction does not hold, cannot be justified. So we see here that if we had fitted the regression line, it's not going to be nonlinear. And because it's curvilinear, we can apply the natural logarithm to it. But the problem is that this does not have a straightforward interpretation as it does for linear regression. So p is given to us by 1 over 1 plus e to the power minus a plus bx. But there's a glimmer of light. In this equation here, we see this term a plus bx, which recapitulates for us the equation of a straight line, which reminds us of the linear regression equation. So there's a glimmer of hope. We can do something. And what is that? Let us consider, for example, odds. What is the definition of odds? Odds simply means the proportion with the outcome divided by the proportion without the outcome. So if, for example, the probability of male at a given height is 0.9, then the odds of being male is 0.9 over 0.1, 0.1 being the probability of not being male. And how did we get 0.1? We subtracted 0.9 from 1. So we have 0.9 divided by 0.1. This gives us 9. So the odds of being male at that given height is 9 to 1, which is 9. The odds of being female is given to us as 0.1 divided by 0.9. That is 1 to 9, which is 0.11. But there's a problem now. We would have expected that the odds of being female would just be the complement of the odds of being male. However, when we look at these odds, we see that there's an asymmetry here, because 9 versus 0.11 is difficult to interpret. Ideally, the odds of being male should be the opposite of the odds of being female, but this is not the case, as we can see. So what can we do? We can correct that asymmetry using the natural logarithm. So the natural log of 9 is 2.217. The natural log of 1 over 9 is minus 2.217. So once we take the log odds, we find that this symmetry is restored, because the log odds of being male is exactly opposite to the log odds of being female. And so this logarithm of the odds is called the logit function, and it's represented, as we can see here, as log p over 1 minus p. If we were to plot the graph, if we plotted the graph of this logit function, it gives us a curvilinear shape. And remember the earlier diagram we saw? This is the shape we had. So when the logit is 0, that is when odds is equals to 1, that is p is equal to 1 minus p, right? That gives us the odds of 1, and the log of 1 is 0, right? So logit is 0, so that means there is no difference. So when odds are less than 1, it takes a negative value, and when it's greater than 1, it takes a positive value, just like we saw. So 2.217 versus minus 2.217. We're making progress. And so the logit is a linear function of x. Exactly. So we can rearrange our p equation now, right? So if we had logit of p equals to a plus bx, because this is a linear function of x, this logit, and you look at p here equals to 1 over 1 plus e minus a plus bx. It is clear to us what we can do. So the logit allows the S-shaped curve to be replaced with a linear function for binary dependent variable. So it's the logit transformation that helps us to take that curvilinear relationship and transform it into a linear function of the dependent variable, and that is our logistic regression. So if we had for multiple logistic regression where there are numerous independent variables, the independent variables can be continuous, categorical, or binary. However, the dependent variable must be binary. A continuous variable can be used, right? You can dichotomize it. Even if you divide into two, it can be used, or it can even be used as a continuous variable. So let's look at this. So we have the logit of p, that's the log odds of p, is now equal to a plus b1 x1 b2 x2 b3, so on and so forth. And so we see that this right side of this equation is our regression equation, similar to what we were doing in our linear regression. The only thing that has changed here is that instead of having y here, or p, or the outcome, and remember the outcome in logistic regression is the odds ratio, the odds ratio. So the odds of the event divided by the odds of the non-event, and we are taking the log of it. So the log odds ratio is what we are looking at as the dependent variable in logistic regression. And this transformation, again, to recapitulate, is the logit function, is the log odds. All right, so let's look at this brief example that looks at predictors of lead toxicity. So the variables we have are age, the use of eye pencil, height for age, z-score, sex, and then the constant value. And so if you look at the odds ratio here, the odds ratio here is 0.96, here is 6, here is 1, and here is 1.113, and these are the confidence intervals, right? And this is a coefficient. Now here's the thing, if you took the exponent of this, you will get this. If you took the exponent of this, you will get this. If you took the exponent, that's e raised to power 0.079, you're going to get 1.08. So that's how you transform the coefficient to the odds ratio, by taking the exponent of it. So if b is the logistic regression coefficient for the variable age, then e raised to power b is the odds ratio corresponding to 1 unit change in age. So for every 1 year increase in age, right, the dependent variable is going to have the odds ratio change by this value, e to power b. So for binary variables, e to power b is the odds ratio of the characteristic assigned value of 1 compared with that assigned value of 0. And so that's how you interpret odds ratio for categorical variables. Alright, so model building refers to deciding on the variables that provide the best prediction of the outcome. So the methods include what we call fault selection and backward elimination. So you start by putting all the variables you'd like to explore in the model, and then you need to limit the number of variables in your model to the number of subjects in your sample divided by 10. I think I'd mentioned that in an earlier lecture. And so you put all the variables you would like to explore in the model, and then variables that you would like to control for as confounding variables should be retained in the model. And so this allows you to obtain adjusted odds ratios because they are adjusted for specific confounders. So you remove the variable with the least significant p-value. That's how you do it. And then you repeat the step, and then you continue to remove variables until all variables in the model are significant. And so this method is what is called backward elimination. And then once you do that, you know the final changes in a statistic known as your negative 2 log likelihood. So negative 2 log likelihood. So but this is not something you're going to do manually. Software is going to do it for you almost automatically. So the important thing is for you to understand the approach you used and how to interpret the model. There are other approaches we could use. We could use forward elimination or forward regression. We could use what is known as hierarchical regression. So there are different approaches, but the simplest one is that you can easily understand is backward elimination. So what is that negative 2 log likelihood that I mentioned? It's a badness of fit indicator, badness of fit in quote. So a larger number means that the model is not very good. It's a poorly fitted model to the data. So the difference between the values of your negative 2 log likelihood is known as the likelihood ratio. So as you are doing your backward regression but elimination, so you do the first model, you check the negative 2 log likelihood, you do the next model, check, and then you look at the difference. So if the negative 2 log likelihood does not change much upon removing a variable, then that variable adds little to the model and can be dropped. So generally, if the difference in the negative 2 log likelihood between two models that differ by one variable is less than 3.84, that's the chi-square value that corresponds to p equals to 0.05, then the difference in the models is not significant. So in our practical sessions, we're going to see demonstration of this and help us to understand better what this means. And then collinearity is also an issue. So if the independent variables are highly correlated with each other, they are said to be collinear. So height and weight are highly correlated, and so they are collinear. And so if there's collinearity, the regression coefficients can become inflated. So the observed value may be far from the true value. So we can only include one of the variables in the predictive model, and typically the one that has the greatest predictive value. So we can't put both of them in the model, right? So you just pick one, the one that has the greatest predictive value, and then you feed that into the model. Then for categorical variables with more than 2 values, you have to recode them as dummy variables. You can't simply code them as 1, 2, and 3 because they'll be treated as numeric values. And this is one of the problems that one sees when we see analysis done, especially using SPSS, which does not offer automatic recoding into dummy variables. So you need to be aware of this. It will not make sense that the second and third categories are equal to 2 and 3 times the value of the first, because these are not numerical variables. They are categorical variables with several levels. So we've already looked at how to create dummy variables in an earlier lecture, but to reiterate or recapitulate, a categorical variable with k values must be coded into k minus 1 dichotomous dummy variables that each have 2 values, 0 value indicating no or least exposure, and then 0 is also the reference value, and 1 indicates the presence of that particular value. So for example, location. So you had a study that had subjects from 3 different locations: urban, semi-urban, and rural. And so this is how we would do the dummy coding. So we create dichotomous dummy variables for location. Semi-urban and urban will need to replace the original coding, and this is what we have. So what this tells us is that rural is being used as the reference value in this case, because it's 0 here, 0 here, and then this is 1, this is 1, and so that's what it is. So semi-urban, urban. All right. So two dichotomous dummy variables are enough to locate the three initial values of location variable. So in the logistic regression model, only the urban and semi-urban will appear. The risk computed for each will be in reference to urban. Interaction means that the odds ratio for a variable varies with the value of another variable. So for example, if the outcome is renal failure, the effect of hypertension will differ greatly between blacks and whites. So renal failure equals to race plus hypertension does not tell the whole story, and another term called an interaction term is needed, and this interaction term is race times hypertension. So renal failure equals to race plus hypertension plus race times hypertension. So this term here is the interaction term. Interaction must be addressed early in forming a model, because the model must contain all single variables as interaction terms to be hierarchically well structured. So what does that mean? You cannot put an interaction term in a model without putting the original single variables that form the interaction term. So all pertinent interaction terms must be evaluated for significance before eliminating any individual variables. We shall see more of this during our practical sessions.